Hello everybody, my name is Cole and this is the 12th video in the UP1 Final Exam Study Guide, and today we're going to talk about the force-potential energy relationship. So this is something that is really certainly going to show up on the final. There's going to be like at least one question where they're going to give you like a graph, and they're going to graph force versus potential energy, and they're going to ask you to like interpret it in some way. So it's an easy relationship, but it's important that we know it. So let's start off with actually a derivation for this, because this is something that is possible to derive. So we're going to start off with writing the equation for conservation of energy. Okay. Now we did this recently, so I'm just going to breeze through it. I'm going to say that kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final plus any work done by non-conservative forces. Now you'll notice that I've done something here a little different from what I wrote last time and what's on your equation sheet. On your equation sheet we have a few more terms. We've got this UG and this U elastic. What I've done is I've combined those potential energies into one term, just all total potential energy. And I can do that because I can do whatever I want. This is my video. So what I want to consider is like a closed system, a system where we're not losing any energy to non-conservative forces. So let's cross out this term. Let's assume this term is 0. We're going to assume that. Assume. Okay, so now what's the relationship between potential energy and kinetic energy? Well, what I'm going to do is I'm going to move things over. I'm going to move all the kinetic energy to one side and all of the potential energy to the other side. So I'm going to subtract KEF on both sides. And I'm going to subtract PEI on both sides. And what I'm left with, is that KEI minus KEF is equal to PEF minus PEI. Well, what's this? These are changes. These are deltas, right? Remember that delta anything, delta x, is equal to XF minus XI, final minus initial, okay? So on this side, we have PEF minus PEI. That's just delta PE. On this side, we have something a little different. We have the initial minus the final. But what I can do is I can just multiply it by -1, okay? And now I have -1 times KEF minus KEI, right? I can multiply it by -1 and then make this negative and this positive. Okay, so the relationship that I end up with is that negative delta KE is equal to positive delta PE. In other words, any energy gained in kinetic energy is energy lost in potential energy, and vice versa within a closed system where you don't lose any energy to non-conservative forces. This is a really important relationship. The way I'm actually going to write it is that delta KE is negative delta PE, just for our proof, but what I've just done there is I've multiplied both sides by -1. Cool. So this is our first relationship. Now I want to take a moment to consider, what do we know about delta KE? Well, we have like an equation with delta KE. We have the work kinetic energy theorem. And that stated that the summation of work done on a system was equal to the change in kinetic energy. Cool, right? So this is our first thing. This is our second thing. Let's combine these two. If delta KE is equal to negative delta PE and also summation work, well then it follows, 1 plus 2, that the summation of work is equal to the negative change in potential energy. Okay, and we're almost there. We just got to rewrite this this left side of the equation really quick. And the way we're going to do that is with the definition of work. Okay. And the definition of work, the calculus definition, if you'll remember on your equation sheet, all the way up, here we go, is F dot dr, the integral of F dot dr. So we're going to have to work in separate dimensions, right? Because these works and these delta PEs, they can be in separate dimensions. But let's say we're working in the x dimension. We can say that the integral from x naught to xf of f in the x direction dx is equal to negative delta PE. This is our force potential energy relationship, okay? More specifically, or more generally, the force exerted in some dimension is equal to the negative derivative. Is that correct? Yes. I'm going to write it with a u, because that's how your equation sheet has it. Negative du dx. Okay. Or, the way we wrote it before, u is equal to negative integral fx dx. Okay? These are your force potential energy relationships. Force is the negative derivative of potential energy, and potential energy is the negative integral of force. This is really cool because these are two values that you would not necessarily immediately see a relationship between, right? It's very intuitive, something like this, maybe, because they're both in joules, they're both units of energy, and if you're like losing some energy, it's pretty intuitive that you're gonna gain some more energy. But force is in newtons, and potential energy is in joules, and this is just a cool relationship. It's not immediately intuitive. So now what I wanna do is just demonstrate just the kind of problem that might show up on an exam, how we can use the force kinetic energy relationship, or sorry, the force potential energy relationship. And the way I'm going to do that is by creating a graph. And on my x-axis, I'm going to have like some displacement, just x. And on my y-axis, I'm going to have potential energy. Okay? And I'm just going to make some little squiggly graph like this. Let's say that's my potential energy versus distance. So now what I can ask you is, I can ask you a bunch of things. I can say, when is F equal to 0? Well, F is du dx. So if this is u and this is x, when is the derivative 0 is what we're asking. Well, when is the derivative 0? At the local maxima and minima. So A, B, C. Okay? So the answer is A, B, C. I could also say, when is F greater than 0? Let's make some more points. Let's go D, E, F, G. Okay? Well, when is F greater than 0? Well, F is greater than 0 when the derivative of u is less than 0. Because remember, f is equal to the negative derivative, right? So if I want f to be positive, the derivative has to be negative. Where's the derivative negative? Well, at E and G. Okay, E, comma, G. Conversely, when is f negative? F is negative when the slope is positive at D and F. Okay? Another really cool thing about this potential energy versus position graph is that it's actually able to be treated as like a track with a ball or a marble rolling around it. This is something that's always been really cool to me. They might ask you a question on an exam that says, when is it at an stable equilibrium versus an unstable equilibrium? So first of all, what does it mean to be in an equilibrium? Well, equilibrium means net force, F net, equals 0. So what are the equilibrium points? Well, they're A, B, and C. We already solved for that. But then what about stable versus unstable equilibrium? Well, stable equilibrium means that if displaced, it moves back towards equilibrium. Okay? That's horrible handwriting, but you get it. And then conversely, an unstable equilibrium would be an equilibrium where if displaced, it doesn't move back towards equilibrium. It will continue rolling far away from equilibrium. So how do we tell which equilibriums are stable versus unstable? Well, there's a mathematical way we could do this, and then there's a visual way we could do this. The mathematical way we could do this is we could say, okay, U is, F is the negative derivative of the potential energy graph. So if I take an equilibrium point and I go left or right, in order for my equilibrium to be stable, I need to have a derivative to the left or the right that will pull me back to the equilibrium point. So if I look at point A and I go slightly to the right, well, the slope of the graph is downwards immediately after the right. If the slope is downwards, that means the force is positive, right? Is that right? Yes. If the slope is downwards, that means the force is in the positive x direction. Well, if the force is in the positive x direction, I'm going to move to the right. So we can see that once I start moving to the right, my force pulls me farther to the right. So this is not a stable equilibrium, because if in order for it to be stable, it would have to pull me back to the left after I start moving to the right. On the other hand, if we look at point B and I go slightly to the right, well, slightly to the right of point B, my slope of the graph is positive, meaning my force is going to be in the negative x direction. And when I move to the right, it's going to pull me back to point B. So point B is stable, whereas A and C are unstable equilibriums. Now, the cool visual way to imagine this is just imagine this as like a roller coaster track, and have a ball or a marble rolling across that roller coaster track. If I put the ball at point A and I push it, is it going to come back to point A? No, of course not. Gravity is going to pull it down, and it's going to keep falling. But if I put the ball at point B and I push it up to point F, it's going to fall back down to point B. So point B is the point of equilibrium where the ball will return to point B. It's the divot in the graph as opposed to a peak. Yeah, so that's just a cool visual thing, the way it works out. I think that's very cool. That's all I have for the force potential energy relationship, and this is right here on your equation sheet. You can see that Fx is negative du dx, and then delta U is negative work, which is negative Fx, integral Fx dx. And that's kind of the end of the first unit. After this, we're going to get into linear momentum and then rotation. So yeah, that's all I have for this, and I will see you next time for linear momentum.